Hello, welcome back to Proximity Math. I'm going to go over the 2005 Aime Ii number 5. Determine the number of ordered pairs a, b of integers such that it satisfies this logarithm equation with a between 2 and 2005 inclusive, and same with b. Okay, so the number of ordered pairs of integers, okay, let me write this down. And also, you should immediately recognize this identity that this is equal to. So log base x of y is equal to log base y of x. This is a simple logarithm identity. And you can also get this by using base change and then taking the reciprocal and then converting it back. Okay. So we're going to be using this immediately. And as you can see here, so what we get is, well, we can substitute x equals log a of base a of b. So that would give us, what's in brackets? Okay, so we have x plus, and this is log base b of a. So using this identity, it's going to be 6 times 1 over x is equal to 5. And then we can multiply both sides by x. I move the 5x to the left side after multiplying everything by x. This is clearly equal to x minus 2 times x minus 3. Alright. So that gives us the two solutions. Alright. So we found the value of log base a of b. So now what? We have two restrictions. We have a and b, both are between 2 and 2005 inclusive. So we have to find the number of ordered pairs of integers that satisfy. We can plug in now for x. So we have to find the number of ordered pairs of integers that satisfy this. Okay, so like they say, first of all, we can raise a to both sides, because log base a of b will cancel out to just b. So if you raise a to both sides, you would get b equals a squared or a cubed. So now all it's asking us to find is the number of integers bounded between 2 and 2005 that satisfy this. In other words, we have to find the number of perfect squares and the number of perfect squares and perfect cubes which are less than 2005. And a must start at 2, because a cannot be 1 apparently. So, okay, squares. First a squared. We're gonna let b equal a squared, and then, okay, so a, something like this. All right, so we can let a be 1. So I'm gonna put this later. Okay, so we can let it be 2, 3, and so on. And obviously, a squared can still be less than 2005. But you should know this as a fact, if you, in case you don't, that 45 squared is 2025. You can like slowly do square roots. Like 40 squared is 1600, so you can slowly increase from there and get to 44. At which point you have 4, 9, blah blah blah. All right. So when it hits 45, we'll have this being greater than 2005. Greater than 2005. And then 44, that's gonna give us that's gonna give us 1936. Right. All right. And you can see that this is the largest A, such that B is still less than 2005 for the case where B is A squared. So we have 2 through 44, which gives us 43 cases for A. And then let's say that it's B is equal to A cubed now for the other solutions. Okay, in that case, what we have is, okay, it starts off 8, 27, and so on. And we need A cubed, which is a B, to be bounded by 2005. Okay. So cubes increase really quickly. And let's see. Okay. What about 8 cubed is 512? 9 cubed 729? No, I have to go higher. Okay. 12 cubed is 1728. You could either know this or work it out for yourself. And then 13 cubed is 2197. And these are small, so it's not hard to do the arithmetic and guess and check. So anyhow, 12 is the biggest A, such that its cube is less than 2005. So that gives us 11 cases from 2 through 12. And then you should definitely not make this mistake. But we have to subtract the cases. Wait, do we? What about the cases where it's a sixth power, you may ask? Because then it would be both a square and a cube. Well, let's see if it's a sixth power. Okay, so like 2 to the 6th, for example. 2 to the 6th is both 8 squared and 4 cubed. But even though it's both a cube and a square, this gives you separate results, separate ordered pairs. So you don't have to worry about overcounting in this case. Just a side note. Okay. Anyway, this is the final answer. 54. Okay. Thanks for watching, and I hope this helped.